Hi, I'm Patrick McFadden. Let's talk about the Linux top command. So the Linux top command is one of those things that ships with every Linux distribution. It can be used anytime you need it to do some really good diagnostics on just system information. So top has been built in to give you those insights into things that you probably don't really find very easily, such as CPU, disk, memory, really important things. And it does give you some insight into how much Cassandra is using or any of the DSE product parts, especially whenever it's a running process. So one of the things that is really important with top is it gives you that full picture of utilization. And let's face it, if you're running a Cassandra node, you pretty much want to see Cassandra eating all of it. You don't want to see anything else taking any of the other time. So this is a good place to start. So let's look at how the command works. So this is the output of when you type the word top in a Linux command line. What you can see here is just a lot of information dumped into one place. And we'll walk through this. But it's broken into really two sections. You have the summary at the top, which gives you an overall picture, the 50,000 foot view or the total system view of what's happening on a running node. And then below that, it gets down to the per process information. So what's happening per running process in user land, in system land, on the Linux node. The first line in that top section is really about how the system is running and how long it's been running. So the current time, so you know what the system time is, and then how long the system has been running, how many users are logged in, and usually that's just gonna be one because this isn't a multi-user system at this point. It should just be you, the administrator, looking at the running node, and then the mystical load average. If you want to learn more about load average, this is not the right place, but essentially this is a figure that shows how much of a load is put on the system based on all the other statistics. Generally speaking, you want to have a load average that's equal to the number of CPUs or less. And in this case, we have three different numbers where we have the 1 minute, 5 minute, and 15 minute mark of how much load average is on there. What we're looking for is a really high load average. If it's much higher than what you expected, you'll see it come through in not the 1 minute, 5 minute, 15, it'll be across the board. If it's a spike, you'll see it really quickly in the 1 minute and not so much in the 15 or 5. So the next line is process information. What you're seeing is how many total are invoked. And then because we're talking about Unix or Linux system processes, there's a concept of whether or not it's running or not. In this case, we have two processes running and 75 are sleeping. That's kind of normal in a large-scale system. A lot of background processes are going to be running periodically, so you'll see them go from sleeping to running. If you have invoked a stop on a process, you'll see it stopped here. Generally speaking, you should see that at 0. And then let's face it, do you really want zombies? No. So let's keep that number at 0 as well. The zombie process, of course, is something that had forked away from another process and is now abandoned. And having zombie processes in your system isn't detrimental, but it isn't a good thing either. The next line is all about CPU information and really critical when you're diagnosing problems with a Cassandra node. So the first part is a user space, and user space is what a user invokes. So if you log into a system and you start a program, that's considered user space. It can also be background that started, say, in a startup. You have something that's invoked when you start the node, such as you're running Cassandra DataStax Enterprise. That would be in user land. System space are those running processes in the background, such as cron or something like that. And those are generally pretty low, but they can be a lot higher if there's something in the system that's running a little hot. Maybe your disk is running too hot. And then the NI is for nice, that's nice processes, but these are low priority. And in running in Linux processes, you can actually assign the priority. If something is in a low priority, it will not run unless there's plenty of free space in the user and system. And this is how we generally run things that aren't a high priority, like for instance, a background process that cleans your disk. Not really high priority, we'll let it run when it can. And then this is the percentage of idle. Basically, this is how much the CPU is just sitting around waiting to do something. Now, this is a really important number for another reason that you would think. CPU wait is an interesting number. And it's not just because you're talking about CPU. It's an interesting thing whenever you're diagnosing a problem in a node. CPU wait is about how much it's waiting to run a process based on something else. Typically, this is it's waiting for something like a disk. And that's a huge problem when you're talking about a database. So if the process is anxious to put something on disk and the disk is like, hold up, can't do that just yet. Well, that's where you're going to start seeing it in the CPU wait, because the CPU has a process that needs to do something and it's being told no. And that number should be 0. If it's not 0, it's time to figure out why. Hardware interrupt and software interrupt are more or less just subnumbers behind that wait. They give you some idea of what's going on. Like, are we waiting for hardware or waiting for software? These are diagnosing numbers as well. And finally, steal percentage, which is a funny number to see. That is also something that you should be watching, and that has a lot to do with virtual systems. If it is not able to get CPU time based on another virtual system stealing away some of the CPU, you're going to start seeing it here. And if you're in a virtual system, this is one you want to watch pretty heavily. The next line has all the memory information. So the first is just a total memory. How much memory do I have physically in the system? So in this case, I'm getting a really large number, great. But if I look at the total amount of used, I'm going to use that as a subtraction. And then that's where you get freed. So you have the total versus used versus free. The buffer count is how much of the memory is being allocated to essentially caching the file system. Now that's really crucial with a Cassandra system because we do a lot of reads, and the SS tables are immutable. So they can be cached really easily. So we see that number going up quite a bit. The last section is about swap. Now, if you look at these numbers, this is how much total swap is allocated. Now, in this case, there's 0, none, and that's okay. We generally recommend no swap. Swap is that area on disk that we can page out physical memory. So if you're starting to run out of total physical memory and you need a little more, instead of just crashing your system, it will page out least used pages into the disk. Now, that is not a good idea. The speed compared from a disk to physical memory is an order of magnitude, but it is meant as a safety valve. In some cases, it's not a bad thing because you have things that are rarely used, like in userland. But for a running server system, having swap can be pretty detrimental, especially if you start bleeding over and using a lot more disk when your Cassandra nodes needs to use a lot of disk. So you get these things working against each other, you're in trouble. So these numbers give you an indication of what's happening. Now we've allocated 0, we have no used and no free, awesome. But we also have our buffer cache, like how much system space is being used for caching the file data. That's an important number to know as well. The next section, the larger section, is about the individual processes themselves. And this is where you get into diagnosis about specific running processes. The first column is a process ID, the PID. And that is assigned to a running process when it starts. This is assigned by the running Linux kernel, and this is nothing that users can do, but it gives you an idea of exactly the process running in the kernel space. So in the top one, for instance, 7719, that's the number that was assigned for this particular process. And it gives you an idea who the process user was. In this case, root for everything because it started right up. But if there is a separate user, for instance, if you see some background process running from userland, you know that someone is running a process and who's doing it. Then we have the priority. Now the priority is coupled with this other version, which is nice. So if you have priority and nice working together, this is where sysadmins can play around with the running processes and get some better tuning. Most systems just start at full tilt. They run at the highest level and there's no nice to them. This is not generally something that gets messed with unless you're running a multi-user system. How much virtual memory is used, how much physical memory is used, and how much shared memory is used, again, is a composite of all process memory run by that process. So it gives you an idea where the memory is being allocated. Now, in this case, with a lot of virtual memory space, this is not the same as swap, but it gives you some idea of where that memory actually resides. So if it's being swapped out because it has been not least used, that's a good thing. If it is being paged out because it's least used, now you know. And then the state of the process. Again, with a Unix process going all the way back to the beginning of Unix, you have these 3 states: sleeping, running, zombies. Zombies are bad. Let's just avoid those. Remember how to get rid of zombies? Fire. But then sleeping and running, those are going to toggle back and forth. If you have a hot process, it's probably going to be running quite a bit. If you have something that runs periodically, like in this case, collect D, for instance, it'll wake up, do some things, go back to sleep. And it's kind of like that process that always runs continuously in the background. It's not going to be running technically all the time. It's going to be waking up, doing some things, going back. Then we talk about CPU percentage, and this is where we start seeing some very interesting things. The next two numbers are the things you want to dial in on. For instance, if you have a running process and it's running at 100% of the CPU, that's good to know because you want to see that that process is eating every bit of that node. Same with memory. If you have something that's taking 100% or more, and it can with swap, you want to know that. And these are important things to see whenever you're trying to diagnose a running system. Now, let's say that it was collect D that was running 100% of the memory or 100% of the CPU. Collect D is a background process. If it's eating up all the CPU, I kind of want to know that. And you can see that here. Then when we get to the timing, this is how much time it's been in a running state. So this gives you an idea how much system time it's actually taken. So for instance, if you have something running at 100% and it's eaten up all the system time since it's been invoked, that's a problem. And then at the end, we have the command name itself. So this is what somebody typed or was in a script. This is the actual running program that was started. Now, you can dig further into these processes with other commands, but this gives you an idea of exactly what program is running in that process. So we have collect D in Java, for instance. Of course, that's what we want to run. Java is usually preceded in front of Cassandra or DataStax Enterprise because it is a Java process. So that's how you'll see it whenever it's presented here. Hopefully this gives you a really good idea of how top works and a good overview. Of course, the Linux man page is going to give you a ton more detail, but this is a good start.